Until recently, more human beings had traveled to the moon than had descended to the deepest parts of Earth's oceans. That comparison sounds impossible, but it reveals something deeply strange about our planet. We have sent astronauts hundreds of thousands of kilometers into space, yet enormous regions of the world beneath our own oceans remain almost completely unknown. Thousands of meters below the waves, sunlight disappears, temperatures plunge, and the pressure becomes so intense that ordinary machines can be crushed or disabled in an instant. And somewhere in that permanent darkness lies one of the most extreme environments on Earth, the Puerto Rico Trench. Before we go any further, please subscribe to the channel and help us reach our goal of 5,000 subscribers. Because what researchers have discovered in the Puerto Rico Trench suggests that the deepest parts of our own ocean may be just as mysterious, and in some ways, just as terrifying as the world beyond Earth. North of Puerto Rico and the Virgin Islands, the seafloor suddenly drops away into a vast underwater scar. The Puerto Rico Trench stretches across the Atlantic for hundreds of kilometers, and at its deepest known point, the Milwaukee Deep, the seafloor plunges to roughly 8.4 kilometers beneath the ocean surface. To put that into perspective, if Mount Everest were placed at the bottom, its summit would still remain underwater. Down there, the ocean isn't simply deep. It becomes an entirely different world, isolated from sunlight, storms, ships, and almost everything happening on the surface. For decades, however, the Puerto Rico Trench lived in the shadow of a more famous rival. When people imagined the deepest place on Earth, they thought of the Mariana Trench. The Mariana had the legendary reputation, the record-breaking depth, the famous expeditions, and eventually the documentaries and movies that transformed it into a symbol of the unknown. The Puerto Rico Trench had none of that glamour. It sat much closer to populated land, hidden in the Atlantic, receiving only a fraction of the attention given to the great trenches of the Pacific. But its lack of fame didn't mean its dangers were any smaller. In some ways, the Puerto Rico Trench may be even more unsettling because of what lies around it. This isn't an isolated depression thousands of kilometers from civilization. It sits along a complicated tectonic boundary where the North American plate interacts with the Caribbean plate. Far below the waves, enormous sections of Earth's crust are constantly moving, bending, sliding, and grinding against one another. To someone standing on a beach in Puerto Rico, that movement is invisible. Beneath the surface, however, the planet is never truly still. That geological tension has consequences. The region around the trench is one of the most seismically active areas in the Caribbean, and its history contains reminders of what can happen when that hidden energy is suddenly released. On October 11, 1918, a powerful earthquake struck near Puerto Rico. The shaking was devastating, but the danger didn't end when the ground stopped moving. The earthquake generated a tsunami that struck the island's western coastline, killing more than 100 people and causing widespread destruction. For residents on the surface, it was a catastrophe. For scientists studying the region today, it became another piece of evidence showing how closely the Caribbean's geological hazards are connected to the ocean floor. And the threat isn't limited to earthquakes. A sufficiently large underwater earthquake or landslide can displace enormous quantities of seawater and generate a tsunami. Because Puerto Rico and several other islands are located relatively close to the trench, there is far less time for communities to react than there might be after an earthquake occurring thousands of kilometers away. That proximity has made the trench not merely an object of scientific curiosity, but an important part of understanding the region's natural hazards. Yet, for much of modern history, scientists knew surprisingly little about what the bottom actually looked like. The ocean's surface could be crossed by ships every day, while the world beneath them remained almost invisible. Sonar provided clues, but the seafloor was enormous, complicated, and difficult to map in detail. The deepest sections were particularly challenging. Every additional kilometer downward meant greater pressure, colder temperatures, and more demanding engineering. This is one reason robotic technology became so important. Instead of placing human beings inside a fragile vehicle and sending them into an environment capable of destroying it, researchers could send remotely operated vehicles and autonomous instruments into the darkness. Cameras could descend. Sonar could sweep across the seafloor. Sensors could record temperature, pressure, chemistry, and movement. For the first time, scientists weren't simply guessing what the trench looked like. They could begin watching it. And when they did, the Puerto Rico Trench started telling a much more complicated story. The first major explorations. The early 21st century marked an important transition in the study of the Puerto Rico Trench. During research efforts in the early 2000s, scientists began using increasingly sophisticated sonar and remote sensing technology to build detailed maps of the seafloor. The objective was straightforward: determine exactly where the deepest parts of the Atlantic were located, understand the structure of the trench, and investigate the geological processes responsible for creating such an enormous depression. The work was anything but simple. Imagine trying to map a mountain range in complete darkness while hovering above it from several kilometers away. Now imagine that the mountain range is underwater, covered in sediment, broken by faults, and hidden beneath thousands of meters of seawater. That was essentially the challenge facing researchers. Every sonar return represented another piece of a puzzle that had remained incomplete for generations. One of the most important targets was the Milwaukee Deep. For years, scientists knew that the Puerto Rico Trench contained the deepest waters in the Atlantic, but determining the exact depth and location required increasingly precise measurements. Modern sonar surveys helped researchers identify the deepest section with much greater confidence, establishing a point more than 8.3 kilometers below sea level. The number itself is difficult to visualize. At that depth, the pressure is hundreds of times greater than the pressure at the surface. A human being could not simply swim there. Ordinary equipment could not survive without specialized protection. Even the smallest mechanical failure could turn an expensive scientific mission into a race against time. But depth wasn't the only thing that interested researchers. As the maps became more detailed, the geological architecture of the region began to emerge. The trench wasn't a simple hole in the seafloor. It was part of an extraordinarily complicated system of faults, slopes, ridges, and deformed crust. The deeper scientists looked, the more they realized that the shape of the trench was a record of enormous forces acting over geological time. Some of those forces are still active today. The Puerto Rico region lies within a complex plate boundary where the North American plate moves relative to the Caribbean plate. Unlike a simple boundary where one plate moves neatly beneath another, the geometry here is considerably more complicated. Sections of the boundary involve subduction, while other areas involve sideways or strike-slip motion. That combination creates a geological environment capable of producing earthquakes and deformation in ways that are difficult to predict. For scientists, this was a crucial realization. The trench wasn't simply an old scar left behind by ancient geological activity. It was part of a living system. Every earthquake, every shifted layer of sediment, and every deformation of the seafloor could provide another clue about how the Earth's crust behaves. The trench essentially became a natural laboratory, allowing researchers to study processes that normally take place far beneath the surface and over enormous periods of time. And the implications extended far beyond geology. A better understanding of the trench meant a better understanding of the earthquake and tsunami risks facing Puerto Rico and neighboring regions. Researchers could use information about faults and seafloor structures to improve hazard assessments, while governments could use those assessments to strengthen emergency planning and warning systems. The discovery of dangerous geological structures so close to populated islands changed the way the trench was viewed. It was no longer simply a remote place where scientists could collect interesting data. It was connected directly to the safety of millions of people. Yet the deeper researchers looked, the more questions appeared. Detailed mapping revealed rugged terrain, steep underwater slopes, fractured rock, and complicated structures that couldn't always be explained from surface observations alone. The maps showed where the seafloor dropped away, but they couldn't immediately explain every process shaping it. A two-dimensional image could show the scars, but not always the story behind them. And that distinction mattered. The Puerto Rico Trench was beginning to look less like a static feature and more like a dynamic system. Sediments moved down steep slopes, faults shifted, earthquakes altered the seafloor, water carried material into the deepest regions. Over millions of years, these processes had created a landscape that remained almost completely hidden from human eyes. Then came the technology that allowed scientists to go beyond mapping. Instead of looking at the trench from above, researchers could finally send cameras directly into it. That changed everything. Entering the darkness. A map can tell you where a mountain is. It can't tell you what it feels like to stand beside it. The same was true of the Puerto Rico Trench. For years, scientists could study sonar images and geological data, but there was something fundamentally different about seeing the sea floor directly through a camera. Suddenly, the trench was no longer an abstract depression on a scientific chart. It became a physical landscape. Remote vehicles descended into the darkness carrying powerful lights, cameras, sensors, and robotic equipment. As they moved downward, the familiar blue of the ocean disappeared. At first, there was still enough ambient light to distinguish shapes. Then the darkness became absolute. The vehicle's headlights became the only source of illumination. Beyond those narrow beams, there was nothing. No sunlight, no horizon, no visible surface, just black water extending in every direction. Then the sea floor began to appear. Rock formations emerged from the darkness. Steep walls rose beyond the cameras. Sediment covered portions of the bottom like an enormous layer of dust. In other areas, the terrain appeared fractured and uneven, shaped by the constant interaction between tectonic forces and the movement of material down the slopes. For the scientists watching from the surface, every new image represented something they had never seen before. And the strangest realization was perhaps the simplest one. This world had been sitting there all along. Above it, ships crossed the Atlantic. Cities continued their daily lives. People walked along beaches without ever realizing that only a relatively short distance offshore, the seafloor descended into one of the most extreme environments on the planet. The deeper the exploration continued, the more obvious it became that the trench wasn't lifeless. In fact, the darkness concealed an ecosystem. A world without sunlight. For centuries, humans tended to imagine the deep ocean as a barren wasteland. The logic seemed obvious. Plants need sunlight. Plants form the foundation of most familiar ecosystems. Therefore, without sunlight, how could a complex ecosystem exist? The discovery of life in the deep ocean destroyed that assumption. Far below the surface, organisms have evolved to survive conditions that would kill most creatures within seconds. They endure crushing pressure, near-freezing temperatures, darkness, scarce food, and a chemical environment unlike anything encountered on land. Some creatures generate their own light through bioluminescence. To a camera descending through the Puerto Rico Trench, those flashes can appear almost supernatural. A tiny point of blue appears in the darkness, disappears, and then returns somewhere else. A gelatinous animal drifts through the beam of a camera, its transparent body barely visible until its internal structures catch the light. There is something profoundly unsettling about watching life move through a place where humans cannot survive unaided. Yet these creatures aren't monsters. They're specialists. Every feature of their bodies represents an adaptation to an environment that has been shaping them for millions of years. Their physiology allows them to function under enormous pressure. Their metabolism is adapted to limited food. Their senses operate without sunlight. Some depend on falling organic material from the surface, while others are connected to chemical processes occurring deep beneath the seafloor. And this is where the Puerto Rico Trench becomes more than a story about depth. It becomes a story about the limits of life itself. If organisms can survive in complete darkness, under crushing pressure, and in chemically extreme environments, then perhaps life is far more adaptable than humans once believed. The deep ocean became a natural experiment for a much larger question. If life can survive under such extreme conditions on Earth, could similar forms of life exist somewhere beyond Earth? Scientists studying potentially habitable worlds such as Europa and Enceladus have long considered the possibility of subsurface oceans. Those environments are radically different from Earth's oceans, but they raise the same fundamental question: does life require sunlight, or can it survive using entirely different energy sources? The Puerto Rico Trench cannot answer that question by itself, but every organism found in Earth's extreme environments expands our understanding of what life is capable of becoming. And that may ultimately be the most extraordinary discovery hidden beneath the Atlantic. The trench isn't simply a deep hole. It is a geological archive, a natural laboratory, a habitat, and a warning. Its rocks preserve evidence of enormous forces that have shaped the Caribbean. Its faults remind us that the Earth's crust is constantly moving. Its depths reveal organisms capable of surviving conditions that once seemed impossible. And its proximity to populated islands makes understanding it more than an academic exercise. But even after the maps improved and the cameras descended, the Puerto Rico Trench still refused to give up all of its secrets. For every answer researchers found, another question appeared. What else was moving in the darkness? What other organisms had evolved beyond the reach of sunlight? What geological structures remained hidden beneath the sediment? And how much of the trench had humanity actually seen? The uncomfortable answer was almost nothing. We had mapped portions of it. We had sampled parts of it. We had sent machines into its darkness. But compared with the enormous scale of the trench, our exploration remained little more than a series of brief visits to a world that had existed long before humans ever looked beneath the waves. And that realization changed the meaning of every new dive. Scientists weren't simply exploring an empty space. They were opening a door into one of Earth's last great unknowns, the Puerto Rico Trench, into the living darkness. By 2015, the Puerto Rico Trench was no longer an empty space on a map. Years of sonar surveys had revealed its enormous depth and complicated geology. But researchers still lacked something crucial: direct, high-definition observations from the depths themselves. That was about to change. The National Oceanic and Atmospheric Administration's Okeanos Explorer arrived in the region with technology capable of reaching deeper, seeing farther, and transmitting what it discovered almost instantly. This wasn't simply another expedition. It represented a new era in deep ocean exploration, one in which scientists no longer had to wait weeks or months to analyze what a remote vehicle had seen. They could watch the discoveries unfold in real time. For people watching from shore, the experience was almost surreal. On computer screens around the world, robotic vehicles descended through kilometers of black water, while powerful lights illuminated small sections of the seafloor. Robotic arms moved cautiously through the darkness. Cameras passed over cliffs, ridges, sediment fields, and fractured rock. Scientists sitting safely aboard the research vessel could communicate with the pilots, examine the footage, and decide where to investigate next. The deepest parts of the Atlantic were suddenly being explored in front of a global audience. As the remotely operated vehicles descended beyond 6,000 meters, the landscape became increasingly alien. There were no familiar signs of the surface world, no trees, no sand beaches, no sunlight, and no horizon. Instead, the cameras revealed a jagged terrain carved by tectonic forces and sediment movement. Massive slopes disappeared into darkness, while ridges rose from the bottom like underwater mountain ranges. Some sections of the seafloor looked broken and disturbed, as though enormous forces had recently rearranged the landscape. Those observations raised an important question. Was the seafloor simply displaying the scars of ancient geological events, or were some of these changes recent? Researchers noticed displaced sediment and disturbed rock formations that suggested movement had occurred at some point. The cause wasn't immediately obvious. It could have been an underwater landslide, sediment collapse, or a small tectonic event that wasn't easily detected from land. Whatever had happened, it reinforced one important fact. The trench was not a frozen relic of Earth's past. It remained a dynamic environment. The deeper the vehicles traveled, the more dangerous the terrain became. Steep cliffs rose from the seafloor, narrow ridges cut across the trench, and loose material covered portions of the slopes. A remotely operated vehicle couldn't simply move wherever it wanted. Every maneuver had to be calculated. A collision with rock could damage the vehicle, while disturbing unstable sediment could reduce visibility to almost nothing. In an environment where communication with the surface already required a long chain of equipment and cables, even a minor mistake could end an expensive expedition. Then there was the sound. At these depths, the ocean isn't truly silent. It contains vibrations, biological noises, distant ship activity, and the deep rumble of geological processes. Sensitive instruments can detect sounds that human ears could never perceive directly. Low-frequency signals can travel enormous distances through seawater, allowing researchers to monitor events happening far beyond the reach of cameras. Some of the sounds recorded during deep ocean research were described as eerie, low-frequency rumbles and groans. Scientists couldn't simply label every sound as something mysterious. Many could potentially be explained by known geological or biological processes. But the recordings demonstrated how active the deep ocean really is. Even when the cameras showed an apparently motionless landscape, the instruments were detecting a world full of vibrations and movement. And then something changed. The cameras began to reveal signs of life. For generations, humans imagined the deepest ocean as a place where almost nothing could survive. The logic seemed unavoidable. Sunlight disappears long before reaching these depths. Temperatures remain extremely low, and the pressure becomes enormous. On the surface, most familiar ecosystems ultimately depend on energy from the sun. Without sunlight, it seemed reasonable to assume that the food chain would eventually collapse. But the deep ocean had a different solution. As the cameras moved through the darkness, tiny points of light appeared. At first, an unfamiliar glow could easily be mistaken for an artifact from the vehicle's lights or a reflection from suspended particles. But some of the lights moved independently. Others appeared, disappeared, and pulsed through the darkness. They were alive. Bioluminescent organisms have evolved the ability to produce light through chemical reactions inside their bodies. In the darkness of the deep sea, that ability can serve many purposes. It can help attract prey, confuse predators, communicate with other organisms, or create a brief distraction that allows an animal to escape. For a creature living several kilometers below the surface, a flash of light can be as meaningful as a shout, a warning signal, or a weapon. Some of the organisms encountered in deep water appear almost transparent. Their bodies are delicate, allowing researchers to see internal structures that would normally remain hidden. Others resemble drifting ribbons or pieces of translucent material floating through the water. Then there are jellyfish, whose bell-shaped bodies and long tentacles can appear almost ghostly when illuminated by the lights of a remotely operated vehicle. The sight is beautiful, but it also reveals something important. The deep ocean isn't empty. It is populated by organisms that have spent millions of years evolving specifically for conditions humans once considered impossible. Among the most recognizable deep-sea scavengers are amphipods. At shallower depths, amphipods can be tiny, shrimp-like animals that most people would never notice. In the deep ocean, some species become dramatically larger. Certain giant amphipods can reach lengths of several centimeters and possess powerful mouthparts designed to process food in an environment where meals can be rare. Their role is essential. The deep ocean receives a constant rain of organic material from above. Dead organisms, fragments of plants and animals, microscopic particles, and other biological material slowly sink through the water column. Much of this material eventually reaches the seafloor. Scavengers, such as amphipods, help break it down, recycling nutrients and keeping the deep ecosystem functioning. In that sense, they are the trench's cleanup crew. But scavenging isn't the only way life survives down there. One of the most remarkable discoveries in deep ocean science has been the existence of ecosystems powered not by sunlight, but by chemistry. In areas where mineral-rich fluids escape from the Earth's crust, hydrothermal vents can create isolated biological communities, unlike anything found on the surface. These vents form where seawater interacts with hot rock beneath the seafloor. The water can become enriched with minerals and chemicals before returning through cracks in the crust. When the hot fluid meets the surrounding cold seawater, minerals can precipitate, creating dramatic structures around the vent. To human eyes, these environments can look hostile. To specialized microorganisms, they can be a source of energy.